Hey Dr. Lane, so I'm going to do a video reassessment on chapter 20. So I'm working on one of the problems from the book, and I can't really, explain it. I mean, I can't really read it, but there's two circuits, and you can see that they're pretty much both the same. Only 4 watts dissipate through circuit 1, and 23 watts dissipate through circuit 2. And it's important to know that the wires and the batteries have negligible resistance. So they're asking us for the resistance of both of them, R1 and R2. So it's important to know that 1 watt is equals to volts squared over omega, which is resistance. So if we just rearrange that, formula, we could figure out circuit 1 and circuit 2, the resistance for both. So that's what I did there. They're asking us for the electric field, and they're giving us the length and the diameter of the wire. So we can use the loop rule and say EMF minus electric field times the length of the wire is equal to 0. So if we just plug in what we have, which would be 10 volts minus electric field times the length of the wire equals 0, and rearrange that, we can get our electric field, which is going to be 2,500 volts divided by meters. And then they're going to give us a third circuit, which looks like this. This is kind of like both of them, both circuit 1 and 2 put together, and they're asking us to graph the potential as a function. So this is what I got. It would increase from the beginning, and then it would drastically decrease and kind of plateau across the, I guess you would say, resistor 1 and resistor 2, and see it would decrease again when it got to that flat area of the wire. So next they're going to ask us to refer to circuit 3, and they're asking us the number of electrons entering R1 every second. So we know our formula, I equals V divided by R. So we could just because it includes both of them, we're going to divide our voltage by the total resistance. So if we do that, because it includes both of them, if we do that, we get 0.340 amperes. Now, amperes is the same thing as coulombs divided by seconds, so if we manipulate that, we can just divide by 1.6 times 10 to the negative 19th coulombs and get electrons per second, which would be 2.13 times 10 to the 18th. And it's going to be the same for R2, since it is the same circuit and it's made out of the same wire material and everything. The current's going to stay the same. And then finally they're asking us the power output. So the power output, it can be, there's many formulas for it, but we're going to use because they're asking us to find it in watts, we can use volts squared divided by our resistance. And once again, we have our volts, and resistance to be the total resistance, just like we used it up there. So it would be 29.34 if you added both of them, and we get 3.4 watts. Thank you.